You know that optical instruments use lenses. Lenses use refraction. There are many types of lenses. I'm going to show you the types of lenses in the beginning. And this again must be an easy chapter to go through, provided you're listening, as always. Because we have been using some of these instruments and we know how most of them work. Sometimes we have a combination of lenses. And like I said, many of you are using lenses right now, either glasses or contact lenses. So this is useful stuff. But what I wanted to ask is a lens actually made, or can you make a lens out of ordinary glass? Is the question. And whenever I ask a question, you've got to think before you give the answer. Can we make a lens out of ordinary glass, like from a window pane? Can I get that glass and transform it into a lens? And what do you think? The simple answer is yes. You can turn any transparent material into a lens. All you got to do is reshape its surfaces. Like if you draw a circle on that window pane and cut it out, just a small circle. And if I hold it this way, facing you, you know that both the sides will be plane, correct? So that means it has uniform thickness throughout. That's why it's not a lens. But if you could grind the material so that you grind off more from the edges and grind less from the center, then you know the center part is going to be thicker than the edges, right? You will have a biconvex lens. Because it's convex on both sides, it's biconvex. But if you do the opposite, grind off more from the center and less from the edges, then the central part will be thin. As you go to the edge, it will become thicker. You have a biconcave lens. But if you only grind one surface and keep the other one plane, you have a plano-convex or you have a plano-concave. But if you want to build contact lenses, then you know that the surface of the lens must have the shape of the eyeball. So you need to have it curved. You can't have one surface plane. So that basically gives you the difference between these lenses that you see. I was first talking about biconvex, and you know the central part is thicker than the edges. This is plano-convex. One side is plane, the other is convex. These two are contact lenses because you can see that this side has the shape of the eyeball. Not drawn to scale, of course. And this is plano-concave. One side is plane, the other is concave. That's biconcave. So those are mainly the types of lenses. So that is a good pathway into this chapter. When you look at a convex lens, and if you look at a parallel beam or parallel rays coming onto it, does this look like a converging lens or a diverging lens to you? It's a converging lens, right? So now you see the difference. A concave mirror was a converging mirror. But now, convex lens is a converging lens. In fact, every property becomes opposite. So if you can remember that, it's clear. Very clear. All properties are switched. Whatever properties a concave mirror had, a convex lens is going to have. And whatever properties the other one had, just switch them. Let's go back over the properties. Which one had a real focus? Concave mirror had a real focus. So which one is going to have a real focus here? Convex lens is going to have a real focus. Okay. Which one could produce both real and virtual images? Concave mirror. So a convex lens can produce both real and virtual images. Everything is switched, so it's easy to remember. And what did you know about a convex mirror? It can only produce a virtual image, and it has a negative focal length because it's a virtual focus, right? Therefore, a concave lens can only produce a virtual image. It has a virtual focus. Watch this. Do you see that it's virtual? Because you see that if it's parallel, it's going to diverge, and you have to imagine that it comes from here. So that's why it's a virtual focus. So all properties are switched. Power of a lens. When you define power of a lens, it's the reciprocal of its focal length, but focal length has to be taken in meters. I think that was a question. You saw that. Focal length has got to be taken in meters. Students make a mistake on that. So if I give you the focal length of a lens is 50 centimeters, go ahead, tell me what is its power? 2 diopter. Diopter is the unit of power, because 50 centimeters is 0.5 meter, 1 divided by 0.5 is 2. Is it positive 2 or negative 2? I just said 50 centimeters, which means it's positive, so the power is also positive. So what kind of lens is that? Is that convex or concave? Let's see who can think. It comes out with a positive focal length, positive power. Which lens is it? It's a convex lens. So if it is negative focal length, negative power, it's a concave lens. All right. Now, ray tracing through a lens should be much easier than through a mirror because of what I'm going to tell you. Watch. A parallel ray goes through the focus. We know that that's the same, right? Except that here it's refraction, not reflection. This point is important in a lens. It's called the optic center. There's only one point like that through which if a ray passes, it does not bend. It'll never bend. It just goes straight through, and that'll be exactly at the center if it's symmetrical. If it's curved equally, that's called the optic center. And then this one, it passes through the focus, so therefore after refraction it should become parallel, right? So those are the 3 rays that you can use all the time to get images, and it's so easy to get that. That's easily understood. So that's the optic center, and that is the image. What are the properties of this image now, please? I should have stopped it. Is that a real image or a virtual image? It's a real image. It's inverted, it's magnified, and it's beyond twice the focal length. When I say twice the focal length, you have to picture that if that's the focal length, twice the focal length would be somewhere here, right? Come on, 2f. So whenever you have a lens, you have to also think about 2f, which will correspond to our center. For a concave convex mirror, you have a center, right? So 2f is in place of the center. The law of distances is the same as before, no change. 1 over do plus 1 over di is 1 over f. How much simpler can it get? Magnification is the same. Negative di by do. Now, I wrote a converging lens because what you have is a converging lens. That's why. A converging lens is a convex lens, isn't it? Struggle. If it is, it went back. For a concave lens, this is what's going to happen. I was talking about this ray. It's a parallel one, diverges, appears to be coming from the focal point. And actually they've drawn 3, but you need only 2. Through the optic center. That's all you need, because both of them appear to be meeting here, isn't it? So that's the concave lens. So you get the concave lens there. You get the head of the image there. What are the properties? It's virtual, upright, diminished, and it's always between P and F. It's always between the optic center and the focal length. And there's surely going to be one question on this on exam 4. That's your eye, pulled out because you were not listening to me. Okay, and so what you need to know is, because this is a physics class, what you need to know is just that the iris opening is controlled to control the intensity of light getting into the eye. So that's why when you walk out in the sunlight and suddenly enter a room, for some time you cannot see anything. Because while you're out in the sunlight, the iris opening is really small to protect your eye from the intense light outside. So when you get inside a room, you've all experienced this, right? For some time, for a few seconds, you can't see it because the iris opening has to now get back to being a little bit bigger for you to be able to see. That part does not refract light. What's important is the cornea. This part is basically what refracts light, not the lens in between. So it's the cornea that refracts 90%. The lens only bends it the remaining 10%. Both of them bend it, is what I'm trying to say, but the cornea bends it more and the lens just makes tiny differences. Because the cornea always refracts it the same way. Now the lens adjusts depending on what object you're looking at. If you're looking at an object very close, the lens becomes thick. And that's done by the ciliary muscles there. The lens becomes thick, and therefore you get the focus on the retina. If you're looking at the stars, now the eye lens becomes really thin, and your eye is set to be in a relaxed position. You need to know, eye relaxed means you're looking at a faraway object. Therefore, it's always relaxing to look at the stars than reading a book. That's one of the reasons why we get tired when we watch television or read a book, because the eye lens has to be thick. That is stressful. But when you look at distant objects, it's relaxed. Okay. Just wrote down that the refractive index of the cornea and the lens has a variable refractive index, as you can see. Cornea, that's the refractive index. Then, how many of you know what near point is? Oh, you did not read the text. There is a minimum distance below which you cannot read a book. Try it out. If you get it too close, you can't see anything. So the near point is that distance only beyond which you can see. And for a normal eye, it's 25 centimeters. That's the near point. But for small children, sometimes I see parents who do not know any science. For small children, the near point is like 10 centimeters. That's why in kindergarten, first grade, second grade, you would see them hold their books very close to their faces. Check it next time. They can see it 10 centimeters. But the parents don't understand. They will say, hold it away. No, they can see 10 centimeters. That's their near point. But as you grow older, the near point shifts away, is what I'm trying to say. And when you get really old, like me, no. Then the near point goes to like 50 centimeters. That's why you see older people, if they're not wearing glasses, like their near point is like 50 or 75 centimeters away. You know what I'm trying to say? So by this you understood. So in a problem, if I do not give the near point, it is 25 centimeters. You need to know that. I'm not going to specify that. The near point is 25 centimeters. Well, the far point is how far you can see. Normally, how far can we see? Normally, how far can we see?
Far.
Far is not an answer.
Really far.
Really far is infinite distance away. We can see up to infinity. Do you know how far the stars are? Oh, they're just 1 mile away. They're millions of light years away. You know what a light year is, right? Distance traveled by light in 1 year, that's all. Light travels 186,000 miles in a second. I think this was a quiz question yesterday. It comes to around 10 to the 15 meters, right? That's how far the stars are. We can see it. And then to say that all this came from bacteria, it's being recorded. And all this came from a single cell organism where you have a great eye that can even see infinite distance away is really being nuts, is being crazy. No doctor in the whole world can design a lens that comes even close to the eye lens, even close. LASIK is good. how do you say it, LASIK surgery. But you talk to people who have gone through this, your eye is never the same again. It gets dry all the time after that. And that's such a bad feeling, irritation. Just imagine your eye getting dry. Let's go back to physics. So the near point is infinity. I mean the far point. What did I say? I'm going crazy. The far point is infinity. The near point is 25 centimeters. Okay. What is short sight? How many people have short sight here? I need to close this. It's nearsightedness, short-sightedness, myopia. This is what happens. We'll take it back a little. Oh, okay. Take a look at this. It's basically because of the shape of the eyeball now. It's become oblongated. It's not spherical anymore. So now what you see is, instead of the focal point being here on the retina, do you see this? It's slightly in front. You make it out? Can you make that out? And do you know that these rays are parallel because they're coming from infinite distance away? And instead of focusing on the retina, you have it where? Before. So what type of lens would you use, knowing that you got to take it, the answer is here, that you got to take it further away, isn't it? You got to take it further away. Would you use a converging lens or a diverging lens? It's converging here, isn't it? Do you want it to converge more? do you want it to converge more? Or do you want it to diverge a little? Diverge, correct? So what type of lens would you use? A concave lens. And that shouldn't be a problem for you to understand at all. Now together, the concave lens and your eye lens together will be able to return the focal point back to the retina. Easy. So short sight is corrected using a concave lens. All right. And as I said, far point is not infinity, but it's X meters. Therefore, when you work out problems, the lens produces the image at X meters of an object at infinity. I'm going to repeat that again. What do you want this lens to do? You want to see up to? Good. So an object is at infinite distance. What do you want this lens to do? You want that lens to produce the image at wherever your far point was. All right, let's say my far point was 2 meters. So I can only see up to? So I can see up to 2 meters, correct? So what do? I wear a lens so that even when the object is at infinity, that lens produces the image at 2 meters. And then my eye lens takes it up from there. Let me see your hands if you understood. Thank you so much. Very good. Farsightedness. Farsightedness, hyperopia, hypermetropia sometimes, is exactly the opposite. Now you see that the focal point is further away. So you know you have to use a convex lens to correct it. That is what I try to do. It's not so clean, but you can make out that when you add that lens there, that's the glasses. Those are the glasses you're wearing. Converging, it shifts the focal point from there back onto the retina. So it's corrected using convex lenses. Clear? Now let's get to which point is affected in long sight? Is it the far point or the near point that's affected? It is the near point. For a normal person, the near point is 25 centimeters. But for this person, instead of being 25 centimeters, it becomes what? Does it become 15? Or does it become more than 25? More than 25, correct. So what do you want that convex lens to do? Because that person can, let's say, he can see up to 75 centimeters. Not up to, 75 and beyond, right? Up to infinity. So what do you want that lens to do? When the object is at 25, Because we want him to see objects that are at 25, correct? When the object is at 25, you want that lens to produce the image at 75. You got it. You got it. And there's no cramming that will work on this. You really have to understand. So 25, the image must be at 75. And then because your eye can see anything beyond 75, it'll pick it up from there. So it's corrected using convex lens. Near point is not at 25 centimeters, but say it's at X, right? And therefore, what do you want? You want the lens to produce an image at X meters of an object at 25 centimeters. What's the real difference between a real image and a virtual image? I know when I talk about the rays, if the rays actually meet each other, it's a real image, right? And if they appear to meet, it's a virtual image. But that's not the practical sense. Can somebody give me the real practical difference between a real image and a virtual image? Anybody? I can only give you a few seconds. If you can't, you did not understand, and you should thank him for asking that question.
Can you project the image?
Kelly, say that loudly.
You can project the image.
And then that, what kind of image is that? This image that you, no, I'll still give it to you. He got the difference. The image that you're seeing now, if you're not blind, all of you can see this. This is being produced on a screen. Do you see this? Is it being produced on a screen? Come on.
Yes.
It's a real image. Any image that can be produced on a screen is a real one. That's why he used the word, can you project it on a screen, on a surface? It's a real one. But when you stand in front of the plane mirror and look at your handsome face or your beautiful face, can you get that image projected on a wall? I mean, can you? There's no way. It appears to be there. Can you see it? That's his question. Can you see a virtual image?
Yes.
Hello?
Yes.
Yes. But you know that seeing this image is different from how you see it in a plane mirror. I hope you're getting it, because this is being really projected. The other one, you're seeing it. So yes, you can see a real image. You can also see a virtual image. But the virtual image cannot be produced on a screen. You're only seeing it. So when you're seeing it, it's being produced on your retina, yes, but not on a physical screen.
I have a quick question.
That's again a good question. Why do we say that the image formed on our retina is always inverted? What kind of lens do we have inside the eye? Is it concave or convex? You should have seen the shape.
Convex.
It is convex. What kind of image can a convex lens produce? I'm talking about the eye lens. It can produce both real and virtual, but if it's being produced on the retina, it must be that's a screen, isn't it? What kind of image is that? It's a real image. And all real images by a convex lens are inverted. Hello? What does the brain do? It turns it around for us. Think about it. All this just happened by chance. All the images that we see are actually inverted, but our brain turns it around. And they did a lot of research on this. They had a guy wear lenses that would re-invert this again. Have you read about it, Evie? Yeah, you've read about it. It's a beautiful one for those who have not heard it. And this guy would, in the beginning, see everything upside down. They asked him not to take it off for several days, maybe. And then you know what happened after some days? Again, he started seeing them straight up, upright. But when he took off the lenses, again, they went back to inverted. And then after a few more days, now he would see them upright again. So this beautiful brain that we have in here that came from bacteria and amoeba is able to self-adjust.
So are there people that their brain
A little bit of confusion coming in here, again, if you're not listening. This part is easy to understand. Your magnificent eyes there, that's the object. And surely, you know, this is a virtual image. Can you see it? Yes. Does it appear to be bigger than the object? Yes. So it's magnified. But magnification is going to be defined in an entirely new way. Now, by now, you only know magnification as what? What's magnification? Maybe you don't know. What's the actual definition of magnification? Hello? Don't tell me it's negative di by do. Don't tell me that. What do you actually mean by magnification?
The size of the image is
Yeah, the size of the image is bigger than the size of the object. So what do you mean by magnification is how many times bigger it is. So if the height of the object is 2 centimeters and the height of the image is 10 centimeters, then everybody should know magnification is 5. So that's the definition for magnification. If I didn't give it to you, that's common sense. Magnification is HI by HO. Those who always need equations, write it down. Magnification is height of the image divided by height of the object. I thought you knew that. But that is linear magnification. What we're going to do now is we're going to define angular magnification. We need that in order to understand how a telescope works. All right? Okay. Angular magnification. I'm going to say it one time neatly because the second time won't be so clear. Because I would know that I'd already said it neatly. So what's this? Carefully. Can you make out an angle here? Well, according to this diagram, because you see two similar triangles, that could either be the angle made by the object or it could be the angle made by the image, right? You with me on that? But now I want you to imagine, and this is the tough part, I want you to imagine that the image is in place of the object. Can you imagine that? So in your mind, just shift this image and put it here. Wouldn't it be big here up to this point? In that case, wouldn't the angle made by it be bigger than the angle that the object makes? All right. The ratio of the two is called angular magnification. But when you put it as a sentence, it becomes really confusing. I would have to say angular magnification is the angle made by the image when it is at the position of the object divided by the angle made by the object. Now you understood. Okay, I hope so. So that's a magnifying glass, and magnification is theta prime by theta. And that's theta prime, correct? That's theta prime. And or you could do one thing. Shift the object and put it in the position of the image. That make sense? You have to, come on, you have to either shift the object to the position of the image or the image to the position of the object. It's just a ratio. So in this case, which one did I shift? I shifted the object, put it in the position of the image. And now you see both theta prime and theta, and it should be very clear what angular magnification is. Right. And we can also prove from this diagram, and be with me, that did you know that angle is arc divided by radius? And in these cases, theta is so small, so sine theta could be taken as equal to tan theta. You heard me? Therefore, when you say tan theta, you can just say theta. That's how you get h by d naught. Watch, in the small triangle. Isn't the height h? Isn't this distance d naught? So surely this angle will be h by d naught, and the other one will be h by n. What on earth is n? Near point. Where do you want this image to be? Do you want to see it? So where should it be? It should at least be produced 25 centimeters away from your eye. Come on now. If it's produced inside 25, you're not going to see it. So that's n. Therefore, theta is h by n. When you put both those together, you get n by d naught. N is fixed for everybody, isn't it? Come on. 25. Therefore, magnification depends on d naught. The smaller d naught is, the more magnified it's going to be. But I'm going to give you an exact formula. Keep listening. Did I talk about a relaxed die? What do you mean by a relaxed die? Where is the image? How far? Don't say far, far, far. It's infinite distance. So if it's a relaxed die, d naught is f, you know. When does a lens produce an image at infinity? Only when the object is at its focal point. Isn't everything reversible? If the object is at infinity, where do you get the image? At the focal point. So if the object is at the focal point, where do you get the image? And that's why I put d naught is equal to f. If you make those substitutions into that, what I did is, in place of d naught here, I just substituted f. You can see that, right? And theta becomes h by n as before. Now you get this form. And I wanted you to just remember these two. This one and this one. And tell me the difference. When do you use this or when do you use this? This one comes with a condition. If the question says it's a relaxed die, then what's the formula? So if the focal length of the convex lens is 1 centimeter, what's the magnification? Oh, 25 times. I thought I would hear that fast. So if the focal length is half a centimeter, now you know why we had to define power of lens as the reciprocal of its focal length. The smaller the focal length, what was happening to the magnification? It was increasing, right? That's why the smaller the focal length. What do you mean by small focal length? Watch. Small focal length. It converges right in front, isn't it? Small focal length. If it's a big focal length, it goes. That's another amazing thing, people don't understand. Why do swimmers have to wear goggles? Think. I know every question you just get the answer in 2 seconds. Usually it's wrong. So because we're supposed to live on the land, our eye focuses correctly only when light goes from air into our eye. But when we are underwater, we know light is going from water into our eye. And the relative refractive index changes. Doesn't it? And therefore it's not going to focus on the retina anymore. So underwater, you're not going to be able to see clearly unless you have air trapped before your eye. That's what those airtight goggles do. They trap air so that now it comes out of water, who cares? As long as it goes into air and then goes into your eye, now you can suddenly see all clearly. Woo! Where are those? Just goggles, just air there, showing that we're supposed to live on land, not be swimming throughout summer. Okay, yeah, go. Okay, once you understand it, it's going to be easy. A telescope has 2 lenses, at least 2. The one that's facing the object is called the objective. Same thing in a microscope, right? And the other lens is called the eyepiece. Because it's close to the eye. It's an eyepiece. An objective and an eyepiece. All right. What do we use the telescope for? Not to look into somebody's bedroom. We always use it for looking at objects that are far away, correct? Therefore, the rays are, come on. All right. If the rays are parallel to themselves, but not parallel to the principal axis, as you can see, they will not come to focus, but they will be in the focal plane. Right? Because now you see, if they were parallel and parallel to the principal axis, they would have come to focus here. They would have come to focus here at this point. But that's not happening now. But this is the focal plane if you're watching. Do you understand what I mean by the focal plane? It's still in the focal plane. What is this? What is this point? FO. What do you mean by that? It's the focal point of the objective. Well, that's correct. Because parallel rays come to focus. Come to focus. That explains everything. So that means they should converge exactly at the focal plane, isn't it? So that's why. So when you draw it, you have to be careful. It should be exactly at this. This image will act as the object for the eyepiece. And it will produce the image at this point. That's clear enough. Okay? So the actual object, maybe the stars that you're looking at, is at infinity. The objective produces its image here, exactly at its focal point or focal plane. And that image acts as the object for this. And therefore, that produces, but wait, is that a real image or a virtual image? I mean, I'm talking about the eyepiece. Why is it a virtual image? Because as you can see, this one is inside the focal point of the eyepiece, isn't it? If the object is inside the focus, it can only produce a virtual image. Therefore, because this image, which is the object for this one, is inside its focal point, it can only produce what? A virtual image. Can you get that on a screen? No. But can you see it? Yes. You're looking from behind, of course, and it appears to be here. So that's the final image. How do you calculate the magnification of a telescope? Let me tell you that the magnification of the objective is 5. Just 5. And the magnification of the eyepiece is, let's say, 4. Use your common sense, and what is the magnification of this telescope? Is it 9? Is it 20? Is it 1? Or is it 1.25? And now you don't even know where I got the 1.25 from. 5 divided by 4. So is it 5 divided by 4? Is it 5 plus 4? 5 minus 4? 5 times 4. Common sense. 5 times 4. Because if you know the idea of magnification, you would surely say the first one makes it 5 times bigger, and the second one picks it up from there and makes it 4 times bigger than that. So the total magnification is always the product of the magnifications, not the sum. You're going to have that as a question sometimes, as part of a question. And sometimes I see people just saying, add it up. And after you look at this diagram, I want you to answer this question. Let's see who will answer this. Can you tell me the approximate distance between the objective and the eyepiece? And wait a minute. When you're focusing, do you know what you're changing? You're changing the distance between the lenses, isn't it? Now, if you understood this diagram, you know why we're doing that. Because we need the first image to be exactly at the focus of the objective. And then we need that as well to be inside this. I've tried so much to explain that point. You see that? Otherwise, it won't be in focus. So, going back to my question. What's the approximate distance between the objective and the eyepiece in terms of their focal lengths? The diagram is right before you. What is the approximate distance between the objective and the eyepiece in terms of their focal lengths? The approximate distance. Should I say this 15 times? I'll try. That was the second time. Now the third time.
L.
All right, the third and the last time. What is the approximate distance between the objective and the eyepiece in terms of their focal lengths?
So big F plus O.
One is FO, the other is FE. Although what's written, I think you can make out it's FO and FE. What's the distance between the objective and the eyepiece in terms of FO and FE? Somebody said it. Because now, what's the formula for magnification of this telescope? What is the formula for magnification of a telescope? Because I talked about the distance in terms of focal length, didn't I? There was a reason. Magnification is beta by alpha. The diagram that I picked from here has the angles labeled as beta and alpha. Make sure you understand what those angles are. Beta is the angle that the image makes with the eye. Do you see that? And alpha is the angle made by the object. So just like we did before, theta prime by theta, same thing, beta by alpha. And when you substitute, you get h by fe by h by fo. Finally, the h's cancel out, and then it becomes simply fo by fe. So magnification of telescope is just the ratio of their focal lengths. And if you look at the diagram, you know fo is greater than fe, isn't it? Isn't it greater than fe? It is, just a little bit. Remember that we really do not want the object to be magnified. Just think about it. We're looking at a star. Do you want the image to be bigger than the star is? The star is huge. That's why we have to go in for the definition of magnification in terms of angles. You see that? It can't be now like we did before. Height of the image divided by that makes no sense. Because you don't want the star to be seen bigger than it actually is. So what are we looking for here? We are looking for, this goes into the next chapter. We're looking for what is called resolution, resolving. I'm just giving you an idea of what resolve means.